Hello and welcome. In this video, we will explore two key applications of mathematical induction that are highly relevant to the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to use induction to prove formulas for the nth derivative of a function, and you will be able to use induction to prove statements about divisibility. These are powerful techniques that allow us to prove general statements about sequences, functions, and numbers. Let's begin with our first topic. Our first topic is induction and differentiation. You are already familiar with finding the first and second derivatives of a function. Higher-order derivatives are found by simply differentiating again. For example, differentiating the second derivative, d squared y by dx squared, gives the third derivative, d cubed y by dx cubed, and so on. This process can be repeated to find the nth derivative, which we denote as dny by dxn. Sometimes, when we calculate the first few derivatives of a function, we notice a pattern. This pattern can often be expressed as a general formula for the nth derivative. For instance, consider the function y equals x times e to the power of x. Let's find the first few derivatives using the product rule. The first derivative, dy by dx, is e to the x plus x times e to the x, which simplifies to the quantity x plus 1 times e to the x. The second derivative, d squared y by dx squared, is the derivative of the first derivative. Using the product rule again, we get e to the x plus the quantity x plus 1 times e to the x, which simplifies to the quantity x plus 2 times e to the x. The third derivative, d cubed y by dx cubed, is the derivative of the second derivative. This gives us e to the x plus the quantity x plus 2 times e to the x, which simplifies to the quantity x plus 3 times e to the x. Do you see the pattern? The coefficient of e to the x is always x plus the order of the derivative. This suggests that the nth derivative is the quantity x plus n times e to the x. We can prove this general formula using mathematical induction. Let's formalize this with a worked example. We will prove by induction that if y equals x times e to the x, then the nth derivative is the quantity x plus n times e to the x. The principle of mathematical induction involves three main steps. First, the base case. We must show the statement is true for the first value of n, which is usually n equals 1. Second, the inductive hypothesis. We assume the statement is true for some arbitrary integer k. Third, the inductive step. We use our assumption to prove the statement is also true for the next integer, k plus 1. Let's apply this to our problem. Step 1. The base case. We need to show the formula holds for n equals 1. The left-hand side is the first derivative, dy by dx. The right-hand side is the formula with n equals 1, which is the quantity x plus 1 times e to the x. As we calculated earlier, the first derivative of x times e to the x is indeed the quantity x plus 1 times e to the x. Since the left-hand side equals the right-hand side, the statement is true for n equals 1. The base case is established. Step 2. The inductive hypothesis. We assume the statement is true for some positive integer k. This means we assume that the kth derivative of y is the quantity x plus k times e to the x. This is our key assumption that we will use in the next step. Step 3, the inductive step. We must now prove that the statement is true for n equals k plus 1. Our goal is to show that the k plus first derivative is the quantity x plus k plus 1 times e to the x. We know that the k plus first derivative is simply the derivative of the kth derivative. So the left-hand side, the k plus first derivative, is equal to the derivative with respect to x of the kth derivative. Now, we can substitute our inductive hypothesis into this expression. This gives us the derivative with respect to x of the quantity x plus k times e to the x. We differentiate this using the product rule. The derivative is 1 times e to the x plus the quantity x plus k times e to the x. Now, we can factor out the common term, e to the x. This simplifies to e to the x times the quantity 1 plus x plus k, which is the quantity x plus k plus 1 times e to the x. This is exactly the right-hand side we were trying to prove. So we have shown that if this statement is true for k, it is also true for k plus 1. Finally, we write our conclusion. Since the statement is true for n equals 1, and if it's true for k, it's true for k plus 1, by the principle of mathematical induction, the statement is true for all positive integers n. Let's work through another example to solidify this process. This time, we'll prove a formula for the nth derivative of a rational function. We will prove by induction that if y equals 1 over the quantity 1 minus x, then the nth derivative is n factorial divided by the quantity 1 minus x to the power of n plus 1. First, let's find the first few derivatives to see the pattern. It's easier to differentiate if we write y as the quantity 1 minus x to the power of negative 1. Using the chain rule, the first derivative is negative 1 times the quantity 1 minus x to the power of negative 2 times the derivative of the inside, which is negative 1. This simplifies to 1 over the quantity 1 minus x squared. The second derivative is negative 2 times the quantity 1 minus x to the power of negative 3 times negative 1, which simplifies to 2 over the quantity 1 minus x cubed. The third derivative is negative 3 times 2 times the quantity 1 minus x to the power of negative 4 times negative 1, which simplifies to 6 over the quantity 1 minus x to the power of 4. Notice the pattern. The numerator is the factorial of the derivative number, and the exponent in the denominator is 1 more than the derivative number. This matches the formula we are trying to prove. Now, let's prove it formally. Step 1. The base case. For n equals 1, the formula gives 1 factorial over the quantity 1 minus x squared, which is 1 over the quantity 1 minus x squared. This matches our calculated first derivative, so the base case is true. Step 2. The inductive hypothesis. We assume the formula is true for n equals k. That is, the kth derivative is k factorial divided by the quantity 1 minus x to the power of k plus 1. Step 3. The inductive step. We need to prove the formula for n equals k plus 1. Our goal is to show the k plus first derivative is k plus 1 factorial divided by the quantity 1 minus x to the power of k plus 2. The k plus first derivative is the derivative of the kth derivative. Substituting our hypothesis, we need to differentiate k factorial times the quantity 1 minus x to the power of negative k minus 1. Using the chain rule, we get k factorial times negative k minus 1 times the quantity 1 minus x to the power of negative k minus 2 times negative 1. The two negative signs cancel out, leaving us with k factorial times k plus 1 times the quantity 1 minus x to the power of negative k minus 2. We know that k factorial times k plus 1 is equal to k plus 1 factorial. So our expression becomes k plus 1 factorial divided by the quantity 1 minus x to the power of k plus 2. This is exactly the right-hand side we were aiming for. Therefore, by the principle of mathematical induction, the formula is true for all positive integers n. Now let's move on to our second topic, induction and divisibility. Number theory is a branch of pure mathematics that studies the properties of integers. A common task is to prove that a certain expression is always divisible by a specific number for all integers n. For example, let's consider the expression f of n equals 7 to the power of n minus 1. Let's test the first few values of n, starting with n equals 0. For n equals 0, f of 0 is 7 to the 0 minus 1, which is 1 minus 1, or 0. 0 is divisible by any non-zero integer. For n equals 1, f of 1 is 7 to the 1 minus 1, which is 6. 6 is divisible by 6. For n equals 2, f of 2 is 7 squared minus 1, which is 49 minus 1, or 48. 48 is divisible by 6. For n equals 3, f of 3 is 7 cubed minus 1, which is 343 minus 1, or 342. 342 is also divisible by 6. It appears that f of n is divisible by 6 for all non-negative integers n. We can prove this using mathematical induction. The process is very similar to what we did with derivatives. but the algebra will involve manipulating expressions to show divisibility. Let's prove that 7 to the power of n minus 1 is divisible by 6 for all non-negative integers n. Again, we follow the 3 steps of induction. Step 1, the base case. The problem states that n can be 0, so our base case is n equals 0. For n equals 0, the expression is 7 to the 0 minus 1, which is 0. Since 0 is divisible by 6, the base case is true. Step 2, the inductive hypothesis. We assume the statement is true for some non-negative integer k. This means we assume that 7 to the power of k minus 1 is divisible by 6. We can write this mathematically as 7 to the k minus 1 equals 6 meters, where m is some integer. Step 3, the inductive step. We must now prove that the statement is true for n equals k plus 1. Our goal is to show that 7 to the power of k plus 1 minus 1 is divisible by 6. We start with the expression for n equals k plus 1 and try to manipulate it to use our inductive hypothesis. The expression is 7 to the k plus 1 minus 1. We can rewrite 7 to the k plus 1 as 7 times 7 to the k. Now, we want to introduce the term 7 to the k minus 1. We can do this by adding and subtracting 7. This gives us 7 times the quantity 7 to the k minus 1 plus 7 minus 1. This simplifies to 7 times the quantity 7 to the k minus 1 plus 6. Now we can use our inductive hypothesis. We assume that 7 to the k minus 1 is equal to 6 meters. Substituting this in, we get 7 times 6 meters plus 6. Factoring out a 6, we have 6 times the quantity 7 meters plus 1. Since m is an integer, 7 meters plus 1 is also an integer. This expression is clearly a multiple of 6. Therefore, 7 to the k plus 1 minus 1 is divisible by 6. We have successfully completed the inductive step. Conclusion. Since the statement is true for n equals 0, and if true for k, it is also true for k plus 1. By the principle of mathematical induction, the statement is true for all non-negative integers n. Let's tackle a more complex divisibility problem. This one involves a product. We will prove by induction that the expression n times the quantity n plus 1 times the quantity n plus 2 is divisible by 6 for all positive integers n. This expression represents the product of 3 consecutive integers. Let's see why it must be divisible by 6. First, consider divisibility by 2. In any set of 3 consecutive integers, at least one must be even. Therefore, their product must be divisible by 2. Second, consider divisibility by 3. In any set of 3 consecutive integers, exactly one must be a multiple of 3. Therefore, their product must be divisible by 3. Since the product is divisible by both 2 and 3 and 3 are coprime, the product must be divisible by their product, which is 6. This is the logical reasoning, but we need to prove it formally using induction. Step 1, the base case. For n equals 1, the expression is 1 times 2 times 3, which is 6. 6 is divisible by 6, so the base case is true. Step 2, the inductive hypothesis. We assume the statement is true for some positive integer k. That is, k times the quantity k plus 1 times the quantity k plus 2 is divisible by 6. We can write this as k plus 1, k plus 2 equals 6 meters for some integer m. Step 3, the inductive step. We need to prove the statement for n equals k plus 1. Our goal is to show that the quantity k plus 1 times the quantity k plus 2 times the quantity k plus 3 is divisible by 6. We start with the expression for n equals k plus 1 and try to manipulate it to use our inductive hypothesis. The expression is the quantity k plus 1 times the quantity k plus 2 times the quantity k plus 3. We can rewrite the term k plus 3 as k plus 1 plus 2. Now, we can distribute the term k plus 1 plus 2. This gives us the quantity k plus 1 times the quantity k plus 2 times k plus the quantity k plus 1 times the quantity k plus 2 times 2. Let's rearrange the first term to match our inductive hypothesis. This becomes k times the quantity k plus 1 times the quantity k plus 2 plus 2 times the quantity k plus 1 times the quantity k plus 2. Now we can use our inductive hypothesis. We know that k plus 1, k plus 2 equals 6 meters. Substituting this in, we get 6 meters plus 2 times the quantity k plus 1 times the quantity k plus 2. We know the first term, 6 meters, is divisible by 6. We just need to show the second term, 2k plus 1, k plus 2, is also divisible by 6. The term k plus 1, k plus 2 is the product of two consecutive integers. In any pair of consecutive integers, one must be even. Therefore, their product is always divisible by 2. So we can write k plus 1, k plus 2 as 2p for some integer p. Now let's substitute this back into our expression. We get 6 meters plus 2 times 2p, which is 6 meters plus 4p. This is not necessarily divisible by 6. We need to be more careful. Let's go back to the step where we had 6 meters plus 2, k plus 1, k plus 2. We need to show that 2, k plus 1, k plus 2 is divisible by 6, which means k plus 1, k plus 2 must be divisible by 3. The term k plus 1, k plus 2 is the product of two consecutive integers. One of these integers must be a multiple of 3. This is not always true. For example, if k equals 1, k plus 1, k plus 2 equals 2 times 3 equals 6, which is divisible by 3. But if k equals 2, k plus 1, k plus 2 equals 3 asterisk 4 equals 12, which is divisible by 3. If k equals 3, k plus 1, k plus 2 equals 4 times 5 equals 20, which is not divisible by 3. This means our algebraic manipulation was not the most effective. Let's try a different approach for the inductive step. Let's expand the expression for n equals k plus 1 directly. This expands to k cubed plus 6k squared plus 11k plus 6. Now let's look at our inductive hypothesis. We assumed k of k plus 1, k plus 2 is divisible by 6. Let's expand that. kk plus 1, k plus 2 expands to k cubed plus 3k squared plus 2k. We assume this is equal to 6 meters. Now, let's rewrite our expression for n equals k plus 1 in terms of our hypothesis. We can write k cubed plus 6k squared plus 11k plus 6 as the quantity k cubed plus 3k squared plus 2k plus 3k squared plus 9k plus 6. The first part is our hypothesis, which is 6 meters. The second part is 3k squared plus 9k plus 6. So we have 6 meters plus 3k squared plus 9k plus 6. We know 6 meters is divisible by 6. We also know 6 is divisible by 6. We just need to show that 3k squared plus 9k is divisible by 6. Let's factor out 3k. This gives us 3k times the quantity k plus 3. We need to show that 3k of k plus 3 is divisible by 6. This means k of k plus 3 must be divisible by 2. Consider the product k of k plus 3. If k is even, the product is even. If k is odd, then k plus 3 is also odd plus odd, which is even. So k plus 3 is even. In either case, the product k of k plus 3 is always even, and therefore divisible by 2. Since k of k plus 3 is divisible by 2, we can write it as 2p for some integer p. Substituting this back, we get 3 times 2p, which is 6p. This is clearly divisible by 6. So we have shown that 3k squared plus 9k is divisible by 6. Our full expression is 6 meters plus 6p plus 6. Since each term is divisible by 6, the entire expression is divisible by 6. The inductive step is complete. Conclusion. By the principle of mathematical induction, the product of any three consecutive integers is divisible by 6. Now that we've covered the theory and worked through several examples, it's time for you to practice. Here are 5 IB-style questions that will test your understanding of induction with derivatives and divisibility. Question 1. Prove by induction that if y equals 1 over the quantity 1 minus 3x, then the nth derivative is 3 to the power of n times n factorial divided by the quantity 1 minus 3x to the power of n plus 1. Question 2. Prove by induction that the nth derivative of x times e to the power of 2x is the quantity 2 to the n times x plus n times 2 to the n minus 1, all times e to the power of 2x. Question 3. Prove by induction that 4 to the power of n plus 15n minus 1 is divisible by 9 for all positive integers n. Question 4. Prove by induction that 11 to the power of n minus 6 is divisible by 5 for all positive integers n. Question 5. Prove by induction that 2 to the power of 3n minus 1 is divisible by 7 for all positive integers n. Pause the video here and try to solve these problems on your own. Remember to follow the 3-step induction process for each one. When you're ready, continue the video to see the fully worked solutions. Welcome back. Let's go through the solutions to the practice questions. Solution to question 1. We need to prove that if y equals 1 over the quantity 1 minus 3x, then the nth derivative is 3 to the n times n factorial, divided by the quantity 1 minus 3x to the power of n plus 1. Base case n equals 1. The first derivative is 3 times 1 factorial over the quantity 1 minus 3x squared, which is 3 over the quantity 1 minus 3x squared. This matches the derivative calculated using the chain rule, so the base case is true. Inductive hypothesis. Assume the formula is true for n equals k. That is, the kth derivative is 3 to the k times k factorial, divided by the quantity 1 minus 3x to the power of k plus 1. Inductive step. We need to prove the formula for n equals k plus 1. The k plus first derivative is the derivative of the kth derivative. We differentiate 3 to the k times k factorial times the quantity 1 minus 3x to the power of negative k minus 1. This simplifies to 3 to the k plus 1 times k plus 1 factorial, divided by the quantity 1 minus 3x to the power of k plus 2. This is the formula for n equals k plus 1. The inductive step is complete. Conclusion. By induction, the formula is true for all positive integers n. Solution to question 2. We need to prove that the nth derivative of x times e to the 2x is the quantity 2 to the n times x plus n times 2 to the n minus 1, all times e to the 2x. Base case, n equals 1. The first derivative is 2x plus 1, all times e to the 2x. The formula gives 2 to the 1 times x plus 1 times 2 to the 0, all times e to the 2x, which simplifies to 2x plus 1, all times e to the 2x. The base case is true. Inductive hypothesis. Assume the formula is true for n equals k. Inductive step. We need to prove the formula for n equals k plus 1. We differentiate the kth derivative using the product rule. This simplifies to 2 to the k plus 1 times x plus k plus 1 times 2 to the k. Factoring out e to the 2x, we get the formula for n equals k plus 1. The inductive step is complete. Conclusion. By induction, the formula is true for all positive integers n. Solution to question 3. We need to prove that 4 to the n plus 15n minus 1 is divisible by 9 for all positive integers n. Base case n equals 1. The expression is 4 plus 15 minus 1, which is 18. 18 is divisible by 9. The base case is true. Inductive hypothesis. Assume the statement is true for n equals k. That is, 4 to the k plus 15k minus 1 equals 9 meters for some integer m. Inductive step. We need to prove the statement for n equals k plus 1. We start with the expression for n equals k plus 1 and manipulate it to use our hypothesis. We can rewrite this as 4 times the quantity 4 to the k plus 15k minus 1 plus 4 minus 60k plus 14. This simplifies to 4 times our hypothesis plus 18 minus 45k. Substituting 9 meters for the hypothesis, we get 4 times 9 meters plus 18 minus 45k. Factoring out 9, we have 9 times the quantity 4 meters plus 2 minus 5k. This is clearly divisible by 9. The inductive step is complete. Conclusion. By induction, the statement is true for all positive integers n. Solution to question 4. We need to prove that 11 to the n minus 6 is divisible by 5 for all positive integers n. Base case, n equals 1. The expression is 11 minus 6, which is 5. 5 is divisible by 5. The base case is true. Inductive hypothesis. Assume the statement is true for n equals k. That is, 11 to the k minus 6 equals 5 meters for some integer m. Inductive step. We need to prove the statement for n equals k plus 1. We start with the expression for n equals k plus 1. We can rewrite this as 11 times the quantity, 11 to the k minus 6, plus 66 minus 6. This simplifies to 11 times our hypothesis, plus 60. Substituting 5 meters for the hypothesis, we get 11 times 5 meters plus 60. Factoring out 5, we have 5 times the quantity 11 meters plus 12. This is clearly divisible by 5. The inductive step is complete. Conclusion. By induction, the statement is true for all positive integers n. Solution to question 5. We need to prove that 2 to the 3n minus 1 is divisible by 7 for all positive integers n. Base case, n equals 1. The expression is 2 cubed minus 1, which is 8 minus 1, or 7. 7 is divisible by 7. The base case is true. Inductive hypothesis. Assume the statement is true for n equals k, that is, 2 to the 3k minus 1 equals 7 meters for some integer m. Inductive step. We need to prove the statement for n equals k plus 1. We start with the expression for n equals k plus 1. We can rewrite this as 8 times the quantity 2 to the 3k minus 1 plus 8 minus 1. This simplifies to 8 times our hypothesis, plus 7. Substituting 7 meters for the hypothesis, we get 8 times 7 meters plus 7. Factoring out 7, we have 7 times the quantity 8 meters plus 1. This is clearly divisible by 7. The inductive step is complete. Conclusion. By induction, the statement is true for all positive integers n. In this video, we have seen how mathematical induction is a powerful and rigorous tool for proving general statements. We focused on 2 key applications relevant to the IBAHL curriculum: proving formulas for the nth derivative of a function and proving statements about divisibility. The core process remains the same: establish a base case, form an inductive hypothesis, and then use that hypothesis to prove the next case. The challenge lies in the algebraic manipulation required for the inductive step, which varies depending on the type of problem. Mastering these techniques is essential for success in higher-level mathematics. Keep practicing, and you'll build confidence in applying this fundamental proof method. Thank you for watching.